So today I'm going to talk about the Parity-time symmetry breaking laser and anti-laser. There's no microphone? Okay, I just use this. Fortunately, Professor Laurie already gave a very good introduction, so I don't have to probably give a more detailed, even more. But so I just changed my slides a little bit a few minutes ago, add a little other things at the end that talk about some other metamaterial activities in my group. So photonics in the real space, we see that many examples already that by modulating the index in space, like photonic crystals or metamaterials, we see a lot of applications. Let me see. Okay, I have to flip this. So, for example, let me see. Is this one going? The dielectric photonics, we all know that. Epsilon mu, both larger than 0. Photonic crystals, waveguides, and so on, silicon photonics. And we see many examples of metamaterials or plasmonics where exploit the epsilon less than 0 lective. And also, we see the metamaterials where epsilon mu, both are lective. Okay. Then you have lective refraction and other things. And of course, in this quadrant, at the lower frequency, there's many materials has mu less than 0. So those are some of the examples. We already see the tremendous progress in a real space of the refracting index. Now, there are actually many opportunities in imaginary space. Namely, that in this horizontal space, simply you plot axis as this red arrow, and one side is a loss and the other side is a gain, where this is imaginary, of course. Okay. So, again, I would like to quickly recap what you already see in the last talk. Parity-time symmetry essentially originally is proposed in more quantum field area. That is not specifically for optics. But generally, if you look at the electronic system as an example, that Hamiltonian's time-dependent Schrodinger equation, actually you have this Hamiltonian that if you do parity-time symmetry operation, namely you switched x to the minus x, t to minus t, and that if the Hamiltonian still preserved under the simultaneous operation of parity and time. And that requires these Hamiltonians, first of all, this potential is symmetrical in the real. The real part of the potential has to be symmetrical. The imaginary part has to be asymmetrical. Now, as you already see in Professor Laurie's talk, that for photonic system, there is a strong analog as well, where the Maxwell equation, actually paraxial equation of the diffraction, shows that you can apply the same operation for P and T. And that requires the optical potential here is an index plus the imaginary part of the index. It's a complex number of the index. And now, this real part of the index has to be symmetrical, and imaginary part has to be asymmetrical. So this actually, in fact, if you combine this requirement, that gives you an index, it sort of like has an exponential of the I beta x. So essentially, if you do such a periodical greeting with a gain, loss, gain, loss, gain, loss, one-dimensional or two-dimensional, what you end up with is actually this greeting, unlike a typical greeting we see, when you have a greeting, you have k plus and k minus, both directions, right? Now, this greeting only have one direction, is unidirectional, the beta. So in Fourier space, there is a 1k director, okay? That gives you a lot of interesting properties of this such a PT system where light transport is unidirectional. So I'm not going to get into that. There's many papers, you can check it out. But in general, again, as I mentioned that, this PT system was originally considered in the quantum field theory. In 1998, Dr. Bender from Washington University of St. Louis, he started looking at this because, you know, it's pretty obvious if you have a Hermitian system, essentially you can imagine that's a lossless photonic crystal system only have a real part of the modulation, imaginary part is a 0, okay, lossless. So if you write out Hamiltonian, and that you will find the PT is symmetrical. Of course, this PT symmetry Hamiltonian ends with a real spectrum, everything is good. So it's a symmetrical, symmetry is conserved. Okay. Now, if you look at the non-Hermitian system, namely, you introduce a loss. Now, in this specific case, of course, you can have a real part of the modulation as a symmetrical in respect to the origin, and the loss or gain modulation, the imaginary part of modulation is asymmetrical. Okay, that also gives you the potential symmetry. But in general, this is a special case, of course. In general, when you introduce a loss, and you would imagine that this is Hamiltonians will actually not behave as a PT symmetry, therefore give you a complex spectrum, or you call symmetry breaking. That complex number, we see that many times in plasma, surface plasma, for example, and so on. But however, what's interesting, this common sense actually was challenged in 1998 by Carl Bender, that he said, wait a minute, in specific, actually, this non-Hermitian system, I may find the exception. The exception is if actually this modulation, the real part, imaginary part of modulation in respect to the real part, this contrast essentially. If that's larger than certain threshold, this symmetry do not exist. That's pretty obvious because the loss is kind of dominant. But however, if this contrast is smaller than certain threshold, actually you do have a symmetry. PT symmetry is preserved. Okay, and everything's real, as if you have this Hermitian case. Okay. So actually, in early time, people looking at different systems, especially quantum system, really try to test whether Carl Bender theory is real. Okay. And there are some explorations using electron, but it's hard to find the quantum mechanical system to test such a thing. So really, actually, last 10 years, we see a tremendous of development use optics to do. And many people are making contributions, include Frank Laurie and others. But here, basically, I cite a few papers. These are very early papers, 2007 and so on, and describe what actually PT symmetry, and this is the gain-loss contrast. And this is the real part, and this is the imaginary part, or gain-loss part. And as you can see, at certain point of the contrast, this threshold, and the symmetry is breaking. Symmetry is breaking. And one of the examples they give is this parallel waveguide. Parallel waveguide. Now, one waveguide is loaded with gain, and the other is with loss. And they are next to each other, can be evanescently coupled. Okay. So what you do is you shoot a beam from the one side of the gain side or loss side, whatever. If they coupled, so energy travels through a gain side while coupled into the loss side and couple back and forth. Therefore, at the end of the day, that at exit, both waveguide has certain output, and roughly they are equal. Roughly they are equal. Okay. This is a typical case, and what we could expect. But if actually the gain and loss contrast is very large, and therefore, essentially, one of them is like perfect metal, and their communication or coupling is effectively, reduced. And the gain, actually, the wave primarily travel into one of them, either gain or loss, and they do not follow into the other side. Therefore, this is actually so-called PT symmetry, and where the gain-loss contrast is larger than certain value. Okay. So this is indeed observed later on, which I will show. But interestingly, actually, in fact, actually, all these early papers didn't forget, whether voluntarily or for other reason, cite even early paper that Spanish group Monga. And this paper actually was, I believe, one of the first, probably the first, actually proposed such PT symmetry potential using optics. In general, this is one of the good examples optics solve the problems that quantum mechanically, so far they haven't really found the solution yet, or experimentally. So this is an experiment that you have actually two waveguide. One is doped with iron, the other without. This is the lithium niobate waveguide. Now, when you pump it, one is a loss, one is a gain. As you can see, if you pump at the lower fluence, and both sides, because their coupling is quite effective, PT-symmetry preserved, and both actually waveguide gives out the emission at the end, okay, roughly equally. But when you pump harder at the higher fluence, that the effectively, the gain loss contrast is so high, the cutoff, the coupling between the two waveguide. Therefore, essentially, if you couple first from the gain side and come out from gain side even stronger because it goes through again. So this is one of the interesting example. Now, what about lasers? Well, we know that if you have a laser, like ring laser, and light travels as a whispering gallery mode inside. However, with the size of, this is about 10 or 12 micron, and this can support many kind of mode, actually. You can see, actually, this is the very soft mode coexist in such a ring. Okay. Now, if you pump it hard enough, it will lace. And of course, it will be multi-mode laser, multi-mode laser. There are two reasons, actually, we want to focus on single-mode laser. One is for the applications. Many applications do require a single frequency emission. And second, actually, especially when you scale down the lasers, they are very small gain volume. And I always like to use this example that it's like a finite, a family with a finite income and want to feed the 10 children. And of course, it's hard, right? Now, if you have a finite gain, it's better to focus on one specific mode. It has a single mode emission. So really, the question is, in a typical laser, can we achieve a single mode? Now, of course, somebody here will know, oh, there's intracavity design. There's many other schemes to achieve single mode laser. What I'm going to talk about is using a PT-symmetry to design such a single mode laser. Therefore, one could gain a very significant advantage, especially this type of laser, single mode laser, is regardless of again spectrum bandwidth, because most of them use actually specific mode splitting to do that, and where you lose the bandwidth. So how we do it? Well, the idea is actually to modulate it along the conference of this ring with a gain and loss, gain and loss. So how we do it? So we basically deposit this pad of metal that act as an absorber, okay, and or loss element. And of course, with the germanium to basically compensate additional introduced the mode index change. We want to maintain the mode index everywhere is the same along the conference, the real part. But however, we modulate the imaginary part here and there. They are opposite in actually one is a gain, one is a loss, and perfect in same magnitude. So we want to use the PT-symmetry to control and select specific cavity mode and to achieve a lasing. So as I say, this is a pure gain and loss modulation. The real part is a constant everywhere. So by simple mode analysis, as you can see in such configuration, you will see essentially you can model that as a two traveling wave. One is clockwise, the other counterclockwise, and this is both are whispering gallery mode. Okay, and again, such a cavity support many type of mode. Okay, as you can see, when you solve this equation, you will find actually this. If you modulate, of course, the imaginary part, and you will find the spectrum of the k vector or wave vector, and has two components: real part, as what you see in the regular spring gallery mode, ring cavity. The other is actually they have an imaginary part of the wave vector. And this actually, the two eigenmode of this shows the PT-symmetry breaking with a complex conjugated wave numbers here. More specifically, you can see that if we plot the frequency of the resonance versus the modulation of the imaginary part, okay? And you see the frequency doesn't change. That means actually their real part do not change with whatever you modulate the imaginary part, which is good. And at the same time, the imaginary part of the wave vector, k, is actually start to splitting right at the 0 of the modulation. So one of the mode is a lazy mode, as you can see. And as you increase the imaginary part, and imaginary modulation, I'm sorry, actually, and the other is actually absorption mode. Okay. And of course, this is for the right desired mode. What I mean right desired mode is there are many modes, only one mode actually match such a period we design. Or in the other words, we design the period specifically locking to m equal to 53 mode. Okay. And therefore, for this mode, there are two degenerate modes. One is lasing, the other is absorption. And later on, we'll talk about this absorption mode. In fact, this is actually a coherent perfect absorption. It's not regular absorption, it's a coherent absorption, which is considered as an anti-lasing mode. So one of the interesting things, you can see this actually symmetry breaking occurred right at 0 point of the modulation. So give a tiny little bit of modulation, you will start actually symmetry breaking. And this is due to the very special continuous rotational symmetry of such a ring structure. That gives you actually so-called threshold-less symmetry breaking. So we also did a simulation to show what happened exactly in such a two mode. One is actually a lazy mode. As you can see, so these are the mode profile. Essentially, it's a bunch of standing waves at m equal to 53. Okay, we pick out this one. I will talk about other mode. So if we enlarge this part, what we see here is actually this is the mode profile, and this is where the gain materials, loss materials, and gain materials, loss materials, gain materials along the conference. So essentially, that the gain actually is exactly overlap with the maximum of the field, while the loss actually is overlap with the value or minimum of the field. That essentially the optical mode see most of the ring as a gain structure, Oppositely, in absorption mode, the loss actually a portion of the ring see the maximum of the field, while the gain see the minimum. Therefore, most of energy and dumping to the loss. Therefore, this is absorption. Now, essentially, in this actually two mode, they occur at the same frequency and coexist in the same structure when you pump it. So essentially, this is the lasing and anti-lasing or coherent perfect absorption mode occur at the same time. So what happened to other mode, m not equal to 53, which essentially they cannot match exactly the periodicity of the modulation. Well, you will see, I just give one example, others are pretty much the same, that gain, loss, these are the position of the materials, and you will see actually the loss part correspond some of the valley, some of the peak of the mode, and if you average it out, it's all gain equal to loss, Okay, therefore, this structure acts as a dielectric lossless structure. Essentially, you pump it into a dielectric ring without any gain there. Of course, the photon running through there until their lifetime comes, which determined by the Q of the cavity. So this actually will be way below the lasing threshold because they do not see a specific gain. The gain and loss are compensated. So in terms of fabrication, in this structure, we actually use indium phosphide as a substrate, and we use a multi-layer quantum well of indium gas arsenide phosphide on top as a gain media. And on top of that, this black ring, we use E-beam to deposit this modulation of this chromium, germanium, which are stacking two-layer, bi-layer. Each of them is about 10 nanometers. And again, germanium role is try to compensate the potential change of that gain part of the real index because of you introduce the loss. And alignment is quite essential that we have to control the precision within about 10 nanometers of E-beam lithography. So once the fabrication is done, we start to look at experimentally whether this indeed gives you a single mode. Of course, as you pump, at the lower fluence, that's just fluorescence without much of feedback. As you pump harder, you see the feedback emerge, and eventually lasing occur. And in this light input-output, light curve, you will see actually there's a distinct of the threshold of lasing as well. So indeed, actually, the multi-mode typically a ring laser. Now, by design carefully using a PT-symmetry, essentially a modulation of pure imaginary part of gain loss, you can specifically select. By the way, the real part is not modulated at all. And you can specifically actually induce the single mode lasing. So laser, we all know that. It is, of course, a coherent stimulated emission, and it is often used a cavity to select a mode, and also it corresponds a specific frequency. It's not like fluorescence. And of course, it has a really good directionality. So what is the anti-laser? Well, anti-laser essentially is a time reversal of the laser. If you do time reversal, and that is what happened. Essentially, physically, it is a coherent, perfect absorber. It's an absorption process that involved with a coherence. Okay. So it is coherent, it is a stimulated absorption, and also involved with cavity, and again, it's usually it's a single frequency, also has a directionality. So let me actually quickly review why this is interesting. Well, we will show that this can be actually a very good sensor for a phase. For example, that if you have a semiconductor, that the current actually is really dependent on the incoming beam of the phase. And in this case, you could realize the perfect absorption. So early work of this coherent perfect absorber is actually was proposed by Doug Stone group in Yale, and later on by the same university Wakehouse group, experimentally demonstrated. Essentially, you have piece of materials, okay, here, and you have two incoming beam, one from the right, one from the left. And this, of course, going through the media, whether absorption or not, and they will have an interference inside. Let's say there's an absorption. And now, if these two incoming beam are coherently at same frequency with a given phase, okay, a certain condition of the phase difference, that out beam, whether transmission or reflection, can be totally canceled. Therefore, everything is absorbed. Everything incoming beam from the both sides are absorbed in such a media. So indeed, actually, this idea was demonstrated here, well, as a cartoon here, that you have two incoming beam. The red line represents the reflection, or the beam comes out, whether you call transmission or reflection. And this is absorbing media. And as you can see, this is a coherent perfect absorption. You have to carefully engineer these two, adjust the two incoming beam, the phase actually at specific location. Now, if that's not the right location, of course, you can see the reflection or transmission comes out. And Doug Stone even showed, very interestingly, you have actually multi-directional incoming beam with actually even a weak absorber here. Everything is trapped inside. So, how we can actually consider a system that both itself is a laser, at the same time it's a perfect absorber. Basically, it's a time reversal, inverse process is occur at the same time. So let's take a look at this media. You have input, output, or transmission A, and then the other beam coming from the other side, B, and transmission here. Okay? And we write the transmission of a matrix here, the AL, BL, and A0, B0. And this matrix, scattering matrix, determines what is the physical actually actions taken inside of media in terms of scattering or interactions. So first of all, if we want the laser, what is a laser? Well, we have a gain media here. We pump it from outside, and there's a beam comes out. Okay, there's a beam comes out. So we only take care of the beam comes out. These two, nothing comes in. Okay? So if we look at this matrix, that force, actually we required that M22 equal to 0. Okay? Now, if we have a coherent perfect absorber, it means that there's an incoming beam here, and from both sides, totally absorbed. Nothing comes out. Nothing comes out. Therefore, that requires M11 equal to 0. Okay. Now, if you want both of them at same time, same device, well, you like to have both of them become to 0. Okay. How we can do that? Well, Parity-time symmetry provides such a convenience, where when you design the index, actually, the real part is actually symmetrical in terms of space, and imaginary part actually is asymmetrical. That actually gives you this is complex number law, essentially. I don't write two equations here. And so this, the M, actually 2 equal to M11. If you use this condition, plug into Helmholtz relation. And you will find, actually, when you require one of them, let's say you require a laser, that will be automatically coherent perfect absorber as well. So laser, anti-laser should be coexist under the parity-time symmetry. So, well, whether this is true, we decide to do an experiment. Well, this is the, originally, you see our last word is a ring resonator. Essentially, that already exists, lasing and anti-lasing at same structure. But we don't have actually a very precise fiber experiment to use a taper to extract the reflections and transmissions. Instead, we decide to design a different structure. Essentially, this is a Brock structure. It's a linear structure, one-dimensional linear structure, waveguide structure. And on the top, again, you have modulation of these metal pads. And then the other part is gain, loss, gain, loss, gain, loss. Okay? This is actually GL, GL. So in this structure, now, there are two incoming beams from both sides as input. Now, if these two beams are at -2 pi phase difference, okay, they form actually a standing wave, essentially. Of course, there's a pump from the top. They form a standing wave. This is a probe beam, by the way, this probe beam. So basically, when you pump it, this lasing mode and coherent CPA mode both coexist. One is actually like this, and the other is like this. And over here, the strong field exists on the gain part, and over here, the strong field exists at absorption part, okay, loss part. But now, how you are going to probe it? Well, we're going to shoot the beam from both sides. This is a probe beam. If they are -0.5 pi, okay, what you see actually, they will have a very strong output, What happened is these two beams comes in. They are coherently, but with a 0.5 pi phase difference. They form a standing wave that exactly matches this actually gain part. Essentially, now under the lasing condition, at the linear regime, they actually be amplified. Therefore, these probe signals are greatly amplified. You will see the output as this. When you scan the wavelengths, at the given wavelengths, actually you will see very strong amplification of the probe beam. Now, on the other hand, in the anti-lasing mode, or coherent absorption mode, that if you turn the probe beam as positive 0.5 pi, that form a standing wave essentially will be exactly matched the CPA mode, namely under the loss. Therefore, the photons will be sucked in like black hole there. Therefore, very little output comes out. So we expect these two things, okay, at the same time. So the material design, again, very similar. We have a real part. We try to maintain that everywhere is the same along the 1D waveguide, while the imaginary part is modulates gain and loss periodically. So as you can see, actually, these two modes are very much different, very much the same, except their real, the real part is exactly the same. The real part, the imaginary part is exactly opposite. And the mode size and shape are very much the same as well. So this is the lazy mode. This is the CPA mode. One thing actually I have to mention, that is this device length has certain requirements from the Helmholtz relation, that equation that you will find to make this one equal to 0, that requires cosine k L equal to 0. So essentially, the k equal to imaginary part of a k lot. Essentially, the L has certain length requirement. It's not any length will satisfy this. So with this type of design, we start the same fabrication with E-beam lithography. Again, very precise to make sure the gain loss are perfectly modulated, and real part is the same, and imaginary part is opposite. So this is the device configuration. This is the basically our device. Actually, it's hard to see here, but essentially it's about this length. Okay, it's a CPA laser. Essentially, is a laser, anti-laser coexist in the same structure, and we have 2 input pot, and then we have the monitoring of the intensity of the input, and then we have output, and we define such parameter that is the contrast of output and input. I have to speed it up. Looks like. How much minutes I have?
Not very many.
Okay. All right. So if I pump, actually, again, with a lower pump, that's just a fluorescence. As you pump harder, the feedback established and start lasing. And we also see the threshold around the 3.6 also. So then we start to probe such existence of the laser and anti-laser at the same structure at the same time. And this is the coherent amplification where you tune the 2 probe beam from both sides with a half pi, minus half pi. While you tune positive half pi, you will see the coherent absorption. And interestingly, you see first several signatures here. First of all, their peak actually is pretty much at the same wavelength. It means that the real part matches very well everywhere. Otherwise, these 2 actually peak will be offsetted. Secondly, their amplification is about 15 dB, and absorption is about 15 dB as well. Therefore, this is actually very symmetrical in imaginary part as well. And in addition, we also did the phase measurement of the output beam. This is the intensity, of course. And that also gives you the same signature of such a coherent process for both lasers and anti-lasers. So with that, I probably quickly go through several slides, or I'm running out of time. So about some other metamaterials activities in my group. One of the things we are really looking at is how we can form a structure, symmetry breaking structure, such as this. It's offsetted with a given desired distance, okay? Desired offset by chemical self-assembly, by chemical assembly. That's hard because this is not thermodynamically favorable because all the metal wires, they like to face-to-face, head-to-head, end-to-end, because that gives you maximum, lowers the energy, right? This is not thermodynamically favorable, but statistically, they still can form such a structure in the solution if you have, billions of particles. So what happened is we want to use a material structure to use chemically defined, basically, directionality. Namely, they can form such a structure in a small probability. Most of them are head-to-head, toe-to-toe. But however, once they form such a structure, there's optical properties, okay? They have a resonance. So in this case, actually, there's a specific resonance corresponding to this structure. Now, if you offset this at a different distance, they have a different resonance as well, with different frequency. So what happened is we're going to shining an optical beam, actually, to disassemble whatever undesired structure. Namely, if the structure is assembled, let's say this is a desired structure, but if the structure assembles this way, this is not desired, but however, this is at a different resonance. So we're going to shining a specific frequency actually matches with this, and essentially photothermal effect will disassemble this. Then only actually the right structure will be survived. So what happened is we are shining a white light, burning a hole with a given frequency, with the only frequency left. That is the one we want to, this structure survive. All other structure will be photothermally disassembled. And they keep doing this until we reach relatively desired sort of offset. In this case, offset is about 20 nanometers with a gap of 5 nanometers. So this is one of the sort of self-correction, self-assembly driven by optical resonance, where this resonance is broadband with different structures, only we leave actually burning one hole in the frequency spectrum that is correspond to the resonance of given structure. And the other activities we have been looking at using zero index materials to eliminate the phase matching conditions that is required very much in any of the nonlinear optics. And once this media is zero index, everywhere the phase is the same. Therefore, you do not require such a phase matching condition. Oh, well, it's automatically matched. You don't have to worry about mismatch. There's the other actually topic we have been explore, that is so-called famous Miller rule in nonlinear optics. Miller rule essentially is an empirical relation established the nonlinear property of crystals with the linear response. And Mr. Miller find actually there's a simple Miller delta describe this relation, namely this is how people find the nonlinear crystals. You only measure the linear response and try to derive what is nonlinear response. But the question is this Miller rule really applied to metamaterials? And we really spent some time on this and really discover that answer is no. In general, that we vary, for example, in this case, metamolecular symmetry, we find these two curves, one is experiment, one is theoretical, they mismatch, they do not agree each other. This is due to actually microscopically, there's a mode actually overlap in such a structure. Now in atomic system, the dipole is so small and that automatically match very well, but this structure do have a different mode. You have to care about that, and therefore this nonlinear metamaterials has to be really derived from the nonlinear scattering theory, that this black curve really matches with the experiment from such treatment. And also about metal surface, we explore using the metal surface for quantum vacuum engineering, essentially to break the isotropic nature of the quantum vacuum in air or vacuum. Therefore, you can have multiple emitters to be entangled or achieve a quantum interference. Others I probably skip. Lastly, I'd like to mention this, and this is a theory work we did, and I'm an experimentalist, so very not too much of the theory, but accidentally we tried to do some chiral structure in Brownian motion, and we lead to a very interesting question, whether we can break the time translation symmetry. So in 2012, we published a paper actually together, well, there's an independent group from MIT, Frank Walzak group. We published back-to-back 2 papers and talk about how we can break the time translation symmetry, so-called time crystals. And recently, I think a few months ago, that there's a French group, I forgot the name, but there's a Maryland group, Chris Murray's group, actually, both of them demonstrate experimentally. Finally, I'd like to acknowledge the students, postdoc, contribute to work. Some of them already left, joined the faculty at UPenn and Peking University, and also funding agency. Thank you.
Thank you very much. A question, please.
Absolutely great talk. I don't have questions regarding your results, but I have a question regarding your terminology with relation to the first part of the talk. If we go to fundamental level of fundamental particles, we all know very well that all interaction and all levels from weak interactions to electromagnetic interaction are PT-symmetric, right? So sequential application of P, T, and C completely restore all interactions, right? In electrodynamics, we do not deal with charge conjugation. We do not deal with C. So from fundamental perspective, all interactions in electrodynamics are PT-symmetric, all of them, right? So that meaning that language you use in your presentation and language of particle physics must be reconciled on some level. You use different terminologies, right? Because you speculate and create and demonstrate systems which do or do not obey PT-symmetry. While on fundamental levels, all systems shall obey PT-symmetry. Actually, this is a very old story. And the beginning of 20th century, people start looking on that. And there were a series of publications, in particular, on how to treat material tensors of the media so that they obey PT-symmetry. So I don't know if you have a view on on that thing.
Good point. Actually, in fact, also Frank Lowry talked about it. But I guess, let me clarify that. Indeed, PT-symmetries prevail in many systems. Now, what happened is people see the PT-symmetry breaking in the non-Hermitian system, in quantum systems, in optics later on. Maybe we didn't pay attention to that. So there is actually indeed PT-symmetry breaking for non-Hermitian system. What happened is the whole talk actually the whole business of PT optics start because of Carl Bender. He doesn't do anything with the optics at the time, 1998. He say that, wait a minute, this non-Hermitian system, typically we believe will break the PT-symmetry, will give you a complex spectrum. But however, he found a very interesting threshold. So even for non-Hermitian system, the threshold, below that threshold, still PT-symmetry. Same thing Frank was talking about. So that is where people got excited. Even in the quantum field theory, where they say, well, let's look for experiment system to realize that, or whether electron system or other system. And that is the, whether you call controversy or surprise, where Carl Bender theoretically proposed in 1998. And what? Well, before him, honestly speaking, there's nobody proposed such a threshold. I'm not sure. Frank will agree with me. Yeah, so this is a surprise to that community. Then people in the quantum mechanical system, I know some of my friends in Chicago try to look at electronic system with a low temperature and try to look for, and it was not very successful. It's a very hard problem. Then later on, optics people comes in and say, hey, we may find a possibility to look into this analog and to provide such a threshold. Indeed, that was observed in the couple of experiments, the threshold behavior. But that wasn't exist before 1998. Carl Bender pointed out. Okay. All right.
Perhaps one very quick question, and then, yeah, please.
Yeah, thank you for the talk. You call the absorption mode after breaking, called the anti-lasing mode, or coherent perfect absorption mode.
Right.
Normally, the coherent perfect absorption mode requires some coupling condition balance between the radiation loss and the intrinsic loss, right? Radiation loss and the intrinsic loss should be balanced for the coherent perfect absorption condition, right? Mm-hmm. But in your ring resonator, there are intrinsic loss. But where is the radiation loss? What acts as a radiation loss channel in your ring resonator? That means the. Can you call such a absorption mode as anti-lasing mode? It's quite strange.
Right. So let me explain. So the coherent perfect absorption essentially is the process of the time reversal of the lasing. Now, in specific case, of course, the ring laser will have a certain Q. It's not infinite Q. Therefore, you have a radiation loss. But if you look at the absorption itself, essentially, you first remove the, basically you see how much photon comes into the system, okay? And then, of course, photon has a certain lifetime, you have to take care of that. But within that lifetime, the absorption process is coherently absorbed. Now, let me give you the other example. That was one of the slide we call experiment. That is essentially first experiment without the lasing, but only CPA. So essentially, it's, I believe it's a silicon wafer or quartz wafer, silicon wafer. So you have beam from both sides, perpendicular to the wafer. And normally, you will have some reflection. But if you tune the phase right, I believe it's about pi. And that actually, this absorption, the reflection or transmission are totally canceled out. a matter of coherence and also interference. Well, right. In that case, it's already considered coupling because you can put a matrix here as I did, and you can consider there's a reflection, transmission, but at that conditions, both component goes to 0.
Okay. I'd love to continue this discussion, even extending it to amplified spontaneous emission, if one may. But in the interest of time, we've overrun already. Please do join me in thanking all our speakers again for an exciting session this morning. Thank you very much.